Good morning, everyone, and welcome to the fourth hands-on session of the workshop Nonlinear Structural Mechanics with Python. So, till the last session, we were looking at various concepts such as assembly of the stiffness matrix for bar elements, and then we looked at the derivation of the stiffness matrix of beam elements. We also solved some problems by coding. So, we'll continue where we left in the last session. So, we were looking at the direct stiffness method for beams, and we saw that it has 2 degrees of freedom per node. So then we derived the stiffness matrix by inverting the flexibility relations for a simple beam. Then we looked at some problems. So in the last session, there was some issue. It was giving junk results such as some 10 power 17 or 18. That was because there was an unnecessary indentation here. So in this, where we enforce the boundary conditions and return the reduced KNF. So this this was indented within the loop. So it will be so this was executed within the loop. So after enforcing the first boundary condition, it returned out of the function. So only one of the boundary conditions was enforced and it had a rigid body mode. So it was basically returning junk. So we have to be careful with indentations in Python. So I made the correction and the updated problem is updated code is there in that Google Classroom. So you can find it here. And not sure if, okay, 2 more people have turned in. That's good. Yeah, you can do it. I'll also give some more assignments on the beam elements and frame elements. So beam, if we do frame and truss, it includes beam as a special case. So frame includes beam as a special case. So maybe we can directly get to frame elements. In addition, I have also modified this module 3 code with some helper functions. So there are some functions to help you visualize the deformed shape. So I have added that. And I also added some function to plot the bending moment diagram. So this problem we solved and we checked everything was all right. And this had only one boundary condition at the left support. So we didn't face any issue even when the code was wrong, when the indentation was extra. But here it's different. So here, since we had multiple boundary conditions, we ran into some trouble. So quickly we can solve the problem by hand. We can solve it by hand. So has anyone solved it by hand? Does anyone have a solution? What is the midspan deflection? Okay, no problem. If you haven't done it, no problem. We'll do it. It may take some 5 minutes. So I'll better do it in OneNote. That's better. Sorry. This is continuous beam problem. Okay. And this is the problem. So we have L by 2, L by 2, L. So we have a support here. And you have a midspan loading. P. So this is L by 2, L by 2, and L. So you see that the loading is symmetric. Loading and structure are symmetric. So you can model only half of the beam, right? So how do you do that? How do you do that? So if what are the symmetry boundary conditions? So suppose you have a body and it is symmetric about some line. Sorry, it's not really symmetric.
Normal forces and tangential displacements are zero.
Yeah, so if it is a line of symmetry, along this line of symmetry, the normal, sorry, what you said is actually,
For anti-symmetric.
yeah, that is anti-symmetric. So it's normal displacements and tangential forces are zero. Yeah, so it's a reason you can check, right? Reason is if you do some symmetry arguments, you flip the structure, it has to be the same. So if a point on this line is moving to this, if you flip it, it will move it to the left. But by flipping, you're not changing anything, neither the loads nor the uh, geometry. Therefore, you cannot have any displacement. If this displacement has to be equal to the flipped displacement, it has to be zero. Similarly, you look at the derivatives, then you get a condition on the tangential forces. So, so that's the thing. So here the line of symmetry is here. So along the line of symmetry, the normal displacement should be zero and the tangential forces have to be zero. Which boundary condition makes sure of that? So it is the guided roller boundary condition. So if you have a so guided roller ensures that there is no slope, right? It ensures that the slope is zero, and the slope is zero means the beam essentially remains like this. If the slope is non-zero, it means the beam is actually having a slope here. But if it has a slope, it means there are some points in the cross section which are moving this way and some points which are moving in this way. But if you ensure that the slope is zero, the cross section remains vertical. Therefore, the normal displacements on that plane are zero. And the tangential forces. So what is the tangential force here? The tangential force here is the shear force. So here, tangential force is the shear force. And if you want zero shear force in a beam, you keep a roller, vertical roller. So if it's not allowed to roll, then there'll be some shear force. So it is free to move in the vertical direction. So the shear force at that point will be zero, but the moment will not be zero. So this reduced model, you can make it this way. Right? So this is a reduced model. This is L and this is L by 2. Next, what do? We can analyze it. So what is our goal? Our goal is to find the displacement of this point. Let us call it V. Right? So what is the static indeterminacy of the structure? Is it statically determinate?
Indeterminate.
Indeterminate by degree, by 1 degree, yes. So static indeterminacy is 1. So you can choose anything as a redundant. Let me choose this, the moment here as a redundant. So I can think of it as an overhanging beam with an applied moment, redundant moment M. Okay, so this is fine. And okay, one more thing. What is the applied load? So for applied load, I'll do pink color. Right. So on the full structure, there's an applied load of P. But when you use symmetric boundary conditions, you have for half of the structure, you can say P by 2 acts here and P by 2 acts on the other half. So there is a moment M here and there is a force P by 2. Okay, so what is the next step? Find the bending moment diagram, right? So use principle of superposition. Right. So due to P, what is the bending moment diagram? So sorry, due to P by 2, what will be the bending moment diagram? Sorry, yeah. So this you can take as a combination of the moment M plus P by 2. Just a minute. Just 1 minute. There's someone at my door. Sorry about the interruption. I'm sorry about the interruption. It was some. Hello, am I audible?
Yes.
Yes, sir.
Okay. For some reason, I'm getting that sound of. I'll just rejoin, right? Yeah, sorry. I was hearing that poor network quality sound. I think now it's fine. Is the recording on? Yeah, recording is going on. Okay, so uh, I was saying that you can use the principle of superposition and look at their effects in isolation and add them up. So what is the bending moment diagram for the first case? You can get it quickly. What is it? So there's a moment M applied here. Yeah. So what are the reactions? Can you say? So let's take this point A and B. A and B.
Is M by L
What's the reaction here? Say we'll start with B because it's easier. What's the reaction?
minus M by L?
Minus M by L. Why do you say so? So minus M by L is downwards, right? Okay. Minus M by L and
M by L.
M by L. Perfect. Yeah. So these two have the net vertical force has to be 0 and the net moment has to be M counterclockwise. So this is fine. So can we sketch it? So from the left, bending moment is 0. Here at a distance, as you go away from this, there'll be a positive sagging moment. So let me put it upward. So here the moment will be M. And here we are applying minus M by L, which is kind of, sorry, here the force is downwards, minus M by L. So what is the moment here? If you see a section from the right, it's under constant bending moment. So these two will cancel out. There'll be a zero shear force in this span. So this span will be zero shear force, and the bending moment will be constant. So this is the bending moment diagram. This is L by 2, and this is L. What is the case here? Here, let me use the other color. Start from the right hand side, it will be easy, right? So at a distance x from the right hand side, what do we have? Up to the point B, the moment caused by this will be negative moment, P by 2 into L by 2. So I have a PL by 4. And this is a hinge support, so it has to be 0. Reactions will compute. Actually, it's not even required for getting. So this is negative. So these are the bending moment diagrams. Let's call this one as M1. This one you can call it as M2 of X. What is the next step? How do we find the displacement at the point C? How did we find it yesterday? How do we find displacement at point C? We have the bending moment diagram. Oh, I didn't say what is point C. This is point C. C is the load point.
Using minimum strain energy theorem. So
Yeah. using the minimum strain energy or the Castigliano's theorem. So let me call some Q is equal to P by 2, right? So this I can write it as QL by 2. Perfect. So the displacement at point C is nothing but, right? You can use the Castigliano's theorem. So this will first give you something which is a function both of M and Q. Then you set the rotation at this point should be equal to 0. We'll do it. It's easy. So what is U? So it is dou by dou Q of what is U? Strain energy. It is integral 0 to L m square by 2 EI dx 0 to L plus take x1 from left hand side because there's a discontinuity here. Take x1 from left hand side and x2 from right hand side plus 0 to L by 2 m square by 2 EI dx2. You can do that because these are square and these are just areas under the area under the curve. So you can split the integral, use two different origins for different spans, and you can do it. It's allowed. Okay. So in the first case, what is in the left span? What is the bending moment? So bending moment is a superposition of this and this. So this one is just mx by L. So it is mx by L, and here it is qx by 2, right? Minus qx by 2, the whole square. So this is x1 and 2 EI, you can take it out. You can take 1 by 2 EI out, dx1. And from in the second span, what do we have? It's going from 0 to L by 2. In the first span, it is just m. The second span, it is minus what it is qx, right? So at 0, it is 0. At L by 2, it is ql by 2. So it is just qx. And you have 1 by 2 EI here. And this is x2 dx2. If you want, you can do the differentiation first and then do the integration, or you can integrate first and then do the differentiation. It's up to you. But if you differentiate it first, it's easier. So let's just take 1 by 2 here, so that the order of whatever is inside will come down. Integral 0 to L. So use the chain rule. So you get 2 times mx1, or you say m minus q by 2, m by L minus q by 2, x1. And then you differentiate whatever is inside. So you get another x1 by 2 dx1 plus 1 by 2 EI integral 0 to L by 2. If you differentiate it, you'll get a 2 times m minus qx2. And you differentiate whatever is inside, you get an x2. And you in both the cases, there'll be a minus sign. So put that minus sign commonly out. So you have a minus and a minus dx2. So what else? So then just do the integration. So you get a minus 1 by 2 EI. The first one, it's x square. So you get an m by L. This 2 gets cancelled. Here also the 2 and 2 gets, no. Here it doesn't get cancelled. Let's have it as 2. You get a m by L minus q by 2. L cube by 3. Plus the minus you have taken out. So here it is. Sorry. So this is still, what did I do? So this is just qx1, right? You can't do this. Plus here we can do it. So the first term gives 2x2, which is 2 m L square by 2. So these two get cancelled. Plus 2qx square. So it is 2q L cube by 3. and sorry, it's L by 2. Sorry. So this is limits are L by 2. So it is 2m. X2 integrated will be x square by 2, and it is L by 2 the whole square by 2 minus q. You have 2q x square, so it becomes x cube by 3. So it is L by 2 the whole cube by 3. So this is what? This is the this is the displacement of the node C downwards. Okay, so it is minus 1 by 2 EI ml square by 3 minus QL cube by 6 plus here you will get 2 gets cancelled. So you get plus ml square by 4. Then what? Here you get a 8. So it is minus QL cube by 12. So this is the displacement of the point C, and it is a function of both m and q. But what is m? The point m, at the point C, the rotation has to be 0. So what is theta C? Theta C is dou u by dou m. So take the same expression. So what is dou u by dou m? It is dou by dou m of, I can take the 1 by 2 EI outside. So it is 1 by 2 EI integral x1 going from 0 to L. It is mx1 by L minus qx1 by 2 whole square dx1 plus 1 by 2 EI integral 0 to L by 2 m minus qx2 the whole square dx2. State energy is the same, it's not going to change. Then just take the 2 EI outside, so it's just let me call it 2 EI theta C is equal to dou by dou m of, now do the differentiation. So I can take the can take it inside because the limits don't depend on m. So the first one will return m by L, same thing, 2 times m by integral 0 to L, 2 times m by L minus q by 2 x1, and you differentiate whatever is inside, you get an x1 by L dx1 plus integral 0 to L by 2, you'll get a 2 times m minus qx2, and you differentiate this, you just get a 1. So it is just dx2. Do this integral. So it is what do we get? We get here it is x square. So it is 2 times m by L minus q by 2. So x square, if you get, you'll get L cube by 3. L cube by 3L plus do this integral. You get first 2ml by 2 minus 2x2, if you integrate, you get an L square. So it is QL square by 4. So like collect similar terms, you get a 2ml. Here you get a 2ml by 2. So it is, sorry. Here it is L cube by 3. It's not 2ml. It is 2 by 3 ml. So this is L, numerator is L cube, denominator is L square. So it is 2 by 3 ml plus you get an ml. So it is, put these two together, minus here what do we have? Here it is this 2 gets cancelled. So it is QL square by 3 minus QL square by 3, and here it is QL square by 4. So what do we get? We get this, the rotation is, or 2 EI theta C is equal to 5 by 3 ml minus 7 by 12 QL square. But theta C is equal to 0 because we have a guided roller, which means what do we get? M is equal to 7 by 4. Yeah. So 3, 12 gets 4. So 5 goes down. So it is QL. So it is 7 by 20 QL. So substitute this into our this equation. So wherever you have M, it is 7 by 20. So delta C is equal to, let me copy this. I hope I'm right. There shouldn't be any mistake. So delta C is equal to minus 1 by 2 EI. What is M? It is 7 by 20 QL. So it is 7 by 60 QL cube minus, is this 6? Yeah, 1 by 6 QL cube plus 7 by 80 QL cube minus 1 by 12 QL cube. So what it is? Can anyone find out? It is something QL cube by EI multiplying something. So some constant, what it is. Let's do it. It is actually, let's do it in Python. That's better. So we'll get a fraction. That's fine. So let's do it.
0.02292.
0.02292, is it? With a negative sign?
Positive signs.
You're saying this expression is positive. This whatever is inside is positive. It can't be.
It's negative.
Because these are, this is negative, but when you multiply it with the minus outside, it's positive, right?
Yes, sir.
And you have taken this 2 into account, is it?
Yes, sir.
Okay, then it's fine. So, so this is fine. So Q is actually P by 2. So can you find what it is? Can you just divide it by 2? So it is 0.01146. Sorry, not Q, P. So what did we take P as? We took P as 10, L as 1, EI as 1. So we should, so our code should answer delta C is equal to 0.1146 units, whatever units here. So that's this is the thing. While coding, you can't take care of units. They're all assumed to be in some consistent set of units, right? So it's the responsibility of the engineer to give it in the right set of units. So so let's run it. This was the problem. So yeah, so I didn't change anything in the code except that I've added these two functions which are useful for plotting. So let's run everything. Yeah, it is all completed. Now let us check U.
It's correct, sir.
It's correct, right? So 0.1146. It is this this node. So this is the third node. So third node is 5 and 6. So it is 0.1146. So it is fine. Now if you want to visualize the deformed shape, I have this function. So you just say plot beam. So I'm not explaining how I coded it because this is meant for structural workshop, right? This is just coding. So this you can actually reuse the code for other things, but this is you can understand it easily, right? So just use the code. You need to input nodes, LMs, and then so see the arguments, right? So I have to give nodes, LMs, the displacement field, and a scale factor. So scale factor is when we solve actual problems, when we take say actual materials like concrete or steel, and you solve actual problems, the displacement will be like 1/1000th of the span, and we can't see it clearly. So in that case, we need to scale up the displacement so that we can visualize something meaningfully. So we have a scale factor. But here we have taken artificial values of EI1, L1. So it just gives some easy to visualize things. So I'll put the scale factor as 1. So I need to input the displacements, the nodes and elements information, and what it is? A scale factor. So scale factor I'll take as 1. Yeah. Plot beam not defined. Oh, plot beams. Okay. Plural. Okay. So just plot it. This is what it looks like. If it's too small, make the scale factor 2. Right? So at L equal to 1, you have a support. At L equal to 2, you have a support. And there the displacements are 0. So the dotted line is the undeformed beam, and the red line is the deformed beam. Or even if this is not comfortable, you can even make the scale factor 5 so that it's easy to visualize. But you should understand that the values on the y-axis make no sense. You can only look at the shape of the deflected beam. It's highly exaggerated, so it is all scaled up so that you can easily see the deformation. So we get the maximum deflection below the load, and this is under hogging, this is under hogging, this span is hogging, this span is hogging, and this span is sagging. Now you can also visualize the bending moment. So use this function, plot BMD, nodes, LMs, U. Now, how do you expect the bending moment? In these two spans, you expect it to be hogging. So it should be like negative in the span, in this span and this span. And in the middle span, you need to be positive. And it will have some kink wherever you have the applied load. So let's see if that is the case. And this as expected. So maximum bending moment is at the middle. And this is to scale. This is not scaled up. There's no scale factor. This is to scale. So the maximum bending moment is 1.5 or 1.6 units roughly. Yeah, on about 1.8 units. And the maximum support moment, the negative moment at the support is something like 0.7. And at the ends, you have 0 bending. So this is not just this beam, right? You can also use it for any. So for the cantilever beam problem also, you can try this. You can just play with the code. You see, you can visualize the bending moment and deflected shape for any beam. So that brings us to the end of module 1. We have looked at beam problems, bar problems, assembly, some basic Python programming, and we are all set to start module 2. So this is already shared with you. You can make use of the code. If you have any doubts, you can ask. Or if you want some other demonstration, if you want to look for, say, simply supported beam or something, you can do that. Any doubts?
No, sir.
Okay. Okay. Yeah. So if you really, I can show it for a simply supported beam, but there's nothing. You can say for simply supported, you just have 2 spans. Say simply supported, loaded at the middle. So 0, 1. Nodes are just 0, L, 2L. Let's just take it. Make it 0, L by 2L. These things are not going to change. Boundary nodes are just the first one. In the first one, you restrict displacement, and in the last one, only these two are there. And there are only 2 elements, 3 nodes. So this is the last node is third node. So in Python notation, it's 2. And it's not f of 4, it's f of 2. So f of 1. And the size of this tip 6, perfect. Let's just run it now. So this value is supposed to be PLQ by 48 EI. You can check that. And okay, here scale factor is too much. Let's make it 1. Yeah. What happened? Why is it? Okay, something is 0, 2, 2 false. displacement restraint, rotation free, 0, 6. Oh, sorry, it's not f of 1, it's f of 1 is the moment at node 1. So we are actually looking at the displacement force at node 2. So it's actually f of 2. Yeah, this we have to be careful. So it's node 1. So corresponding to node 1, it is vertical degree of freedom. So that is 2 times 1, which is 2. Yeah, that's a silly mistake. Don't do. Yeah, so this is fine. You have this is the deflected shape of the simply supported beam, and this is the bending moment. So the maximum bending moment is positive. So it is PL by 4. P is 10, L is 1. So it is 2.5. So you can check it for any known beam and compare it with your known answers. Again, yeah, I'm sorry for the mistake. It should be this. We have to be careful while filling. Now I'll close this beam problems. We will start with. Oh, I didn't save it. Save it. I'll close the beam problem, and we'll start with trusses. Truss elements. So first, let's look at the theory. So a critical thing that is different from beams and bars in the case of frames and trusses is the inclination of the members, right? So beam, a bar is straight and it is horizontal. A beam is also straight and horizontal. There is no inclination. So there are no horizontal displacements that we are interested in. We are only interested in, sorry, in a beam, we are not interested in the horizontal displacements. And in a bar, we are not interested in the vertical displacement. Instead, if you have a truss member like this, which is inclined at an angle, even under vertical forces, there will be some horizontal forces in general. So the axis of the member is something, and the global coordinate axis is something. So what I have denoted in blue color, this is the global coordinate system. Global coordinates. And the yellow color one is local coordinates. Right. So locally the axes are inclined. We'll look at the local coordinates. The reason is if you want to look at the strain in this member, how do you find the strain in this member? It is the extension of this member divided by the total length of the member. But the extension of the member, it is easy to calculate in the local coordinate. Say it's easy to represent the extension in the local coordinate than in the global coordinates. So we deal with two sets of coordinate systems. One, which is we call axis aligned coordinate systems. So that coordinate system is aligned with the axis. So the x dash axis is aligned with the center line of the truss or frame member. And global coordinate is something that we are comfortable with. So if we are looking at some roof truss, if you're looking at some kind of roof truss, then naturally we want to have the vertical direction this way and horizontal direction this way, so that the loads, like say wind loads, are like this and gravity loads are like this. So this is a convenience. So the global coordinates x and y are chosen as per our convenience, and local coordinates, there's no freedom. You have to orient it along the axis of the member, center line of the member. Now let us see how do we transfer the forces. So a vertical, say a gravity load will not be, will have both axial component and transverse component on this member. So x dash is the axial axis, y dash is the transverse. This is the axial. How do we transform it? Use the rule of vector addition. So given a vector force F is a vector, it is a directed line segment. It has components in the blue coordinate system like this. So you project it along the blue coordinate system, you get fx and fy. You project it along the yellow coordinate system, you get fx dash and fy dash. Note that the vector itself should not depend on which coordinates you're using. So if you see, there is a relationship between these fx dash and fx and fy. So how do you find fx dash in terms of fx and fy? So resolve fx dash along the this new coordinate system. So the component of fx along fx dash is what? It is fx cos alpha. And what is the component of fy along fx dash? It is fy cos of, if this is alpha, this is 90 minus alpha. So fy cos of 90 minus alpha is fy sin alpha. So fx dash is cos alpha fx and sin alpha fy. Similarly, resolve the components fx and fy along. Okay, I'm talking too much orally. So let's just say so you have two sets of coordinates. This is fx, this is fy, the components of the force in one coordinate system. And this is some fx dash, this is fy dash. So project this fx onto fy. So let's say this angle is alpha and project this onto this. So this fx dash should be sum of fx. So this is alpha, this is 90 minus alpha. So if you project these, you get fx dash is what? It is fx cos alpha plus fy cos of 90 minus alpha. Yeah, so it is basically cos alpha fx plus sin alpha fy. What about fy dash? Project both of them. Now extend this fy backwards. So if we project it, this angle is actually 90 plus alpha. So it is fx cos of 90 plus alpha plus fy. Fy is here. This angle is what? This angle is just alpha. Fy cos alpha. So this is minus fx sin alpha plus cos alpha fy. So how can you represent it in a more concise form? Yes. So put fx dash fy dash is what? It is
Cos alpha, sin alpha,
yes,
minus sin
minus
alpha, cos alpha,
cos alpha.
fx, fy.
Perfect. So what this transformation does, let us call this transformation matrix Q. So the Q matrix takes in the components in xy coordinates, which are the straight coordinates, components in global coordinates, and it returns the components in axis aligned coordinates. Let's call it axis aligned coordinates. So this direction is important. Q takes in the components from the global coordinates and returns the components in the axis aligned coordinates. So that's what I have done here. So fx dash is this the relationship. You call this matrix Q. And U is also a vector, right? The displacement is also a vector. Its components also transform according to the same rule. So you can have axis aligned U and V. So the force you can resolve along the axis, which is fx dash, and perpendicular to the axis, which is fy dash at any point. Similarly, the displacement of every point also, you can have along the axis of the member, which is u dash, perpendicular to the axis of the member, which is v dash. What about the rotations and moments? They will not change with coordinate transformation. So you're rotating the coordinates in the same plane. So rotation is also in the same plane. So it is not going to, so if you say something rotates, some member rotates by an angle theta, it really doesn't matter which theta you don't talk with respect to coordinates. Right? Theta doesn't have components. Theta is a scalar. In plane rotation is a scalar. So it does not change with the choice of coordinate systems. So it doesn't have any components. It's just a scalar. So it doesn't transform. So what is the transformation relation between theta in the unprimed and theta in the global and local? It's same. Just theta global is equal to theta local, theta axis aligned. And similarly, the moment global is equal to moment local or moment axis aligned. Now let us consider a truss element as shown. We know that a truss element cannot resist forces perpendicular to the axis. So F1 y dash is equal to F2 y dash should be 0. What is F1 y dash? It is the transverse load at node 1. So this is node 1. This is node 2. F means force. 1 means applied at node 1. Y dash is the direction. So dash represents you have in this transverse it's in the axis aligned coordinate systems, and y dash is the transverse direction in the axis aligned coordinate systems. So these two have to be essentially 0. So how do our equations change? So in the axis aligned coordinate system, the truss element is a bar element. So in the axis aligned coordinate system, the truss element acts as a bar element, right? Because the axis is the same as the it's rotated so that you have the x-axis oriented along the central line of the truss member, which means it is just a bar element. It can only extend. There's no other degree of freedom. So uh, so we have these relationships. So what is the relationship for bar? Let me use f1x dash, f2x dash. How is it related to the u1 dash, u2 dash?
Stiffness matrix. It is
Yes.
AE by
Well,
L
yeah.
minus AE by F, then AE
And
by
a by it. Now I want to make so this does not depend on v1 dash and v2 dash. Whatever be the transverse displacement, it's not going to cause any axial force because a truss member cannot support transverse loads. So if I want to make the right hand side u1 dash, v1 dash, u2 dash, v2 dash, what should I do? So matrix multiplication has to be compatible. So this is 4 cross 1. Left hand side is 2 cross 1, which is just f1 x dash, f2 x dash. What should I do here? I need a 4 cross 2 matrix. So whatever is multiplying v1 dash has to be 0. So v1 dash has no stiffness contribution. So it is just, I'll take the AE by L out. So it is AE by L. Corresponding to u1, the coefficient is 1. Corresponding to v1, the coefficient is 0. Corresponding to u2, the coefficient is -1. v2, 0. Similarly, with f2, what relates f2 to u1 is -1. f2 to v1 is 0. f2 to u2 is 1. And f2 to v2 is 0. Now let's also make the left hand side a full vector of f1 x dash, f2 x dash, sorry, f1 y dash, f2 x dash, and f2 y dash. If I want to make this, so these two are basically 0. These two are basically 0, but they are unknowns. In general, they are unknowns. So how do I get zeros? Make the entire row 0. So 0 multiplied by whatever thing will become 0. So it's like second and fourth rows are just zeros. And the other two remains unchanged. So by introducing zeros, we have changed nothing. These two systems are exactly equivalent. Actually, they are identical. These two systems are identical. We have only added some zeros and made the size of the matrices 4 cross 1, 4 cross 4, and 4 cross 1. So what is this? This is the stiffness matrix of the, so this relates the forces in the local coordinate system, in the axis aligned coordinate systems, with the displacements in the axis aligned coordinate systems. So this is the stiffness matrix of, so yeah, so this is what I have there. So this is the stiffness matrix of the truss member in the axis aligned coordinate system. Now we already saw that the forces are transforming according to a certain rule. We have this f dash is equal to qf and d dash is equal to qd, where q is this matrix. So why do we have it something like this? This is what we called as q, right? Why do we have it this way? Hello? Somebody's trying to talk, but I'm not getting any voice. Is that?
convert local to global to local.
Yeah, we are converting global to local. That is okay. What I'm asking is why do we have this? So what we had here was we just had cos alpha, sin alpha, minus sin alpha, cos alpha, which is the relationship between the force components in the global and the force components in the local system at any point. But I have repeated it twice. That is a 2x2 matrix. This is a 4x4 matrix. What is the reason? The reason is there are two nodes, right? So I'm doing the so this, if you say if it is multiplying by fx1, fy1, fx2, fy2, you see these two columns will multiply with whatever is there for the first node, and these two columns will multiply with whatever is there for the second node. So the force, when we do the coordinate transformation, we cannot have a force, we cannot have a relation where the force at the first node depends on the force at the second node. So the coordinate transformation is at a point, right? So transformation is at a point, at every point actually, it's at every node. So the coefficients that are relating different nodes, right? So these are the cross coefficients. These are the relations between force at node 1 and force at node 2. So force at node 1 in the local coordinates and the related with force at node 2 in global coordinates. This cannot be there. This has to be 0. So when you do coordinate transformation, you cannot have the force at one point depend on force at some other point, right? It has to be within that point. So this system transforms the force only at node 1. So these two are at node 1, these two are at node 2. So this 2x2 matrix acts on this 2x1 subvector and returns the 2x1 subvector, which is the force at node 1 in local coordinates. And similarly, this 2x2 submatrix acts on this 2x1 subvector and relates and gives the force at node 2 in the local coordinates. So so this is the form of Q, right? It's cos sine minus sine cos. It's just repeated in this format. If you have one more node, you just put another one, right? But we are dealing with two noded elements, so we don't need that. In finite elements, you also have three noded elements. You can have as many nodes as we want. This by increasing the order of interpolation. So there you will have to repeat this transformation matrix along the diagonal as many nodes as we have. So that is fine. Now, the relationship we had was f dash is equal to kd. D dash, right? This was the stiffness relation in the local coordinates. Then we wrote that f dash as qf and d dash as qd using the transformation relations. Now q is an orthogonal matrix. You can check that. If you do q transpose q, you will get identity. Right? If you do q transpose q here, you will get identity, and the determinant of q is 1. You can easily check that. So in this case, you just so the determinant of this will be you can check that. It's quite straightforward. It's very straightforward. You can find the determinant of q. It will be identity. So take this, multiply with it q transpose. You will get the identity matrix. So yeah, you can check that, right? If you just multiply it, you will get cos square alpha plus sin square alpha. Then you get minus sin alpha cos alpha plus cos alpha sin alpha, and so on. So along the diagonals, everywhere you get cos square alpha plus sin square alpha. And along the off diagonal terms, you'll get either 0 or minus sin alpha cos alpha plus cos alpha sin alpha. That's a simple matrix multiplication. You can check that. If you verify that, you'll get Q is an orthogonal matrix. So Q transpose Q is I. So let us pre-multiply on both sides by Q transpose. So you will get Q transpose QF is equal to Q transpose K dash QD. But what is Q transpose Q? It is I. And what is IF? Identity acting on any vector will give the vector itself. So the force in the global coordinates is equal to Q transpose K dash Q D. So D is the displacements in global coordinates. F is the force in global coordinates. And this is relating the displacements and forces in global coordinates. So what is this? What is Q transpose K dash D Q? Something that relates displacements. stiffness matrix. So the truss element stiffness matrix expressed in the global coordinates is this. So it is AE by L is a constant, you can take it out. It is Q transpose K dash Q. So this product will have some weird form. It's like some cos square sine. It has a certain form, but it is easier to code without taking the product, right? Now let us look at the algorithm for coding it. So it is algorithm for truss problems. Now you should be able to tell. What is the first step? What did we do in bar and beam? First step in the algorithm is
Nodes matrix.
yes. What is the first step towards solving? Should I go back? Problem formulation, right? First step, you want to present the problem in a way that the computer can understand. Especially for trusses, it is even more difficult because it's a 2D structure. So you can look at a truss like this and say it is. You can visualize it, draw the forces, but it has to be given in a format that the computer can understand. So you have to do problem formulation. So what all information we have to give in problem formulation?
Nodes.
Notes. So in this case, what will be the notes? How do you, so I'll tell you. Suppose we have a truss like this. This is a node. This is a node. This is a node. And this is a node. This is a node. This is a node. So let's call it node 1, node 2, node 3, node 4, node 5, node 6. Okay, so what is the information about a node? How many pieces of information?
2 pieces of information.
3?
X coordinate, Y coordinate.
Okay, yeah, only 2, right? So x coordinate and y coordinate. So node will be of the form x1, y1, x2, y2, and so on up to xn, yn. So node is a list of tuples, and node is a list of coordinates. So you can specify nodes in this format in Python, no problem. Done. Then what is the second piece of information?
Elements.
Elements, perfect. So next is elements. How do we specify that? What are the elements here? I can number this as element 1, element 2, element 3, 4, 5, 6, 7, 7, 8, 9. Yeah, it's a 9-member truss. So elements, how do I specify the elements?
Node numbers 1,
Yeah.
2,
2, 3.
3.
Yeah, we can have, actually you can write it down. Yeah. 1, 4, then
4, 2.
4, 2. So if you recall, so if you see, you can orient an element this way or this way. So the second element could have very well been 3, 2. But you said 2, 3. So that orientation is important. So first element is like this. Second element is like this. Third element you said 1, 4. So it is like this. Fourth element you said 4, 2. So it is like this. Okay. Then fifth element is, this is the fifth element. You can say 2, 5. Then sixth element is
3, 5.
3, 5. So have the orientation correct. So it's 2, 5, 3, 5. Seventh element is 4, 5.
4,5.
And then eighth element is 4, 6. Ninth element is 5, 6. So this is the element information for this truss. Okay, now this is done. What's the next step?
Boundary nodes.
Okay, so boundary nodes. Let us use the same convention as what we did for beams, because beams also had 2 degrees of freedom per node. Here also we have 2 degrees of freedom per node. Let us say bound nodes is of the form node number
1.
I have not specified the boundary condition yet. So then is there a displacement restraint? Sorry, there it was displacement 1. So there it was rotation and displacement. Here you don't have rotation. Trusses have only displacement degrees of freedom. Say is U1 restraint and U2 restraint. Right. Suppose I gave the boundary conditions like this. This is hinged, and here you have a roller. So this statically determinate. So in this case, what will be the boundary conditions? Yes.
1, restraint.
2, true. Right. Both U1 and U2 are restrained here, and node 3.
False, comma.
Yes.
False, comma 2.
Yes. Perfect. Very good. So this is how we give the boundary conditions. Very good. Then what is the second step? We have defined the problem. Yes.
Initialization of global
Initializing the global stiffness. Global matrices. So let me call the number of nodes as num nodes and number of elements as number of elements. So what should be the size of the global stiffness matrix?
number of degree equal to number of degrees of freedom.
Okay,
That is
so
2
what?
times the number of nodes.
Yes, so number of degrees of freedom is 2 times the number of nodes. And this is number of degrees of freedom comma, number of degrees of freedom. So many things you set it to 0. Then force vector also you set it to 0. Very good. Then what is the third step? Third step. Initialized it. Next, you have to fill it in with the entries. So what is the third step? You have to fill it with entries. Assembly, right? That's what we did in both bar and beam elements. We did that only. So we said we'll do this assembly operation. We'll assemble the global stiffness, right? So we initialized it, then we populate the global stiffness matrix with. So we take every element of the element stiffness matrix and plug it in appropriate positions. So third step is assembly. How do we do assembly? You can tell me how do we do assembly? We loop over what?
Nodes.
No, we loop over elements. Loop over all elements. So what did we do? We had same thing. Only thing is the members are not horizontal now. They are just connected in all other directions. So you have something like this. You take every element. and see where, look at its first node, you see where it will go. Look at the second node, where it will go. Second, take the second element, look at its first node, where it will go. Look at its second node, where it will go. That is how we did, right? Why will it be suddenly elements for, nodes for this case? We loop over all elements. So once we go to an element, what we should do here? What we should do here? In one element, what we should do inside the loop?
Check its node numbers.
Yes. Check what is node 1, what is node 2, corresponding to like first node in the global matrix and node 2. Then what other information we want to construct the element stiffness matrix? We want the length of the element, right? We want the length of the element. How do we find the length of the element? Let's say node 1 is x1, y1. So node 1 is, node 1 is n1 and it has coordinates x1, y1. And node 2 is n2, it has coordinates x2, y2. How do you find the length of the element?
Yes, square root of x2
Square root
minus
of
x1. x2
yes.
minus x1 the whole square plus y2 minus
Whole
y1
square plus y2 minus y1 the whole square.
Yeah, perfect. Very good. So yeah, bar and beam, it is just x2 minus x1. In this case, it is square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. So we need L, we need AE, that I'll give. AE again, as usual, we are going to take it as 1 mostly. And what other information is required for the truss problem? Is this enough? What is the main difference? Alpha, perfect. So how do you find alpha? You have the coordinates. Can you find alpha?
del y by del x.
Okay, so by that, you mean y2 minus y1 by x2 minus x1. Is this alpha?
Tan inverse of
Tan inverse of y2 minus y1 by x2 minus x1. Is this alpha? Now, how does it differentiate between something in first coordinate and something in third coordinate? Because tan inverse will give. So if you have an element oriented like this or an element oriented like this, tan inverse will give the same answer, right? Because tan is positive in both first coordinate and third coordinate, and it is negative both second and fourth coordinate. So we don't know if an element is oriented this way or this way. So how do we differentiate it? We need some way to do it, right? So alpha, how to do that? So you have to take cases. You have to basically take cases. So you find the magnitude of alpha by this one. You just get the magnitude of alpha doing this. Then the actual quadrant you fix it by checking the sign of y2 minus y1 and x2 minus y1. Sorry, x2 minus x1. Look at the sign of these two, then you fix the actual coordinate as, quadrant as 1, 2, 3 or 4. And the magnitude of the angle, you get it from tan inverse of y2 minus y1 by x2 minus. Okay, anything else we need? That's all. Then what is our assembly step? Our assembly step is take a local matrix, see where it will fit in, and put it appropriately. K of some node 1, node 2. This is the basic step, and this is exactly same. We can reuse the code from beam elements. Why? Only the type of the degree of freedom has changed, but the number of degrees of freedom are the same as what we had in beam elements. So that also has 2 degrees of freedom per node. This also has 2 degrees of freedom per node. Only the entries will change, but this relationship between local and global will not change. So you take something where you should fit in, there we had something like 2 times node 1 and 2 times node 1 plus 1. So the same logic will follow, because there are also 2 degrees of freedom per node, here also 2 degrees of freedom per node. Here also two nodes per element, there are also 2 nodes per element. So this will not change. This will be exactly the same as beam code, so I can reuse it. And then what do we do? Third step, or fourth step, what do we do after assembling the full stiffness matrix?
finding the displacements.
No, something is missing before that. Will this be solvable? It will have rigid body modes, right? So I have to enforce boundary conditions. So one check is the seeing a stiffness matrix we get will always be singular. The global stiffness matrix that we assemble will always be singular because it has rigid body modes. So until you give some support conditions for the truss, it is just floating in air. So it will have rigid body mode. So if you apply a small force, you cannot solve for the displacements. It will have infinite displacements. So it will be singular. It cannot be solved. So you should always enforce boundary condition, and it is singular with, say, if you know, the rank of the matrix will be
Less than order.
yeah, it will be less than the order. And how much less than the order? It will be the order minus 3. Because there will be 3 rigid body modes: translation along x, translation along y, and rotation. So this singular matrix will have a rank which will be order minus 3. So of course it's less than order. So enforce the boundary conditions. Therefore, the singular matrix will become solvable. And then finally solve. How do you solve? A inverse f is equal to u. So this is the algorithm. Any doubts? So we'll implement it in 10 minutes. It won't take much time, but we need a Taylor problem, right? So let us solve a simple problem and then we'll implement it. So tell me a quick problem, say benchmark problem, whatever. Any suggestion? So let me take a triangular truss. Statically determine it. I'm applying a load P here. And let it be equilateral. So the dimensions are L, L, and L. So this angle is how much? 60 degrees. Yes, 60 degrees. So quickly you can tell me the member forces. Let me call it ABC. No, ABC. I'll make it 1, 2, 3 so that we can reuse the same degrees of freedom. 1, 2, 3. What is the force F13? It's statically determined, so you can tell me just by looking at the truss what it is. So this is the vertical force of P.
Minus P.
No. It's not minus P. So this it's vertical component of this. Yeah, the reactions are P by 2, P by 2. So the vertical component of this will be what? It will be 2P by root 3. Right. So the net sum. So this will carry P by 2, and this cos 60. Okay, better I'll say F13 cos 60 plus F23 cos 60 is equal to P, right? But F13 is equal to F23 by symmetry. So you can say F13 cos 60 should be P by 2. But what is cos 60? It is root 3 by 2. So F13 root 3 by 2 is equal to P by 2. So F13 is
2 P by root.
no, P by root 3.
2.
So it's 2P by root 3 shared by the 2. So 1 will be half of it. So it is P by root 3. So F23 is also P by root 3. Same. So what is F12? So this member F23 is carrying a force of P by root 3. And there's no other force at this joint. So at this joint, if you draw the force triangle, this is having P by root 3 compressive. This is having some tensile force, which is F12. What is F12? And this has a vertical reaction. What is the vertical reaction? P by 2. So what should be F12?
P by 2 root 3.
No, why is so this is what? This is 60 degrees. It is P by root 3 cos 60 minus F12 is equal to 0, right? So F12 is P by root 3 cos 60, which is root 3 by 2. So it is P by 2. It's not P by, it's P by 2. Is that okay? Hello?
Yes, sir.
Yeah.
Cos 60. Cos 60
Oh, sorry.
is 1 by
Cos 60 is 1 by 2. Right. That's. Oh yeah. This is sines. Sorry. That's good. That's a good catch. So this is cos 30. This angle is 30, right? I made a mistake. This cos 30. 30. Yeah, you're right. So this I made a mistake. So this p by root 3 cos 60. Cos 60 is 1 by 2. Perfect. So this has to be 1 by 2. 2p by root 3. P by root 3 cos 60.
No,
which
sir.
is,
P by 2 root 3.
oh, sorry. Yeah, it's p by 2 root 3. Yeah, sorry for the mistake. Yeah, p by root 3. P by root 3 cos 60 is half of p by root 3, which is p by 2 root 3. Fine. Right. So this will be, so the member forces are p by root 3, p by root 3, and p by 2 root 3. Okay. Next, what do we do? But wait, there is some.
We have to find displacements, sir.
Sorry, you said something. I couldn't.
We have to find displacements at nodes.
Hello?
Sir, we have to find displacements at nodes, sir.
Yeah, we have to find the displacements. So let's just take one node. Others are going to be, let's just take the node 3. Okay, so node 3, if you see, if you will just check against 1. Okay, so node 3 will have a, node 3 is connected to this member 1, 3. The strain in this member is what? It is stress by E, and stress is what? P by root 3 A. So there's an E. This is the strain in the member. And what is the length of the member? L. Change in length of the member will be epsilon L, which is PL by root 3 AE. So at this point is going to move towards this direction by PL by root 3 AE. Right? If you take it as compressive, it's going to move towards this direction by PL by root 3 AE. And this angle is 60 degrees. So this displacement delta L is equal to PL by root 3 AE. What is the vertical displacement? It is some, let's call it delta Y. So
PL by 2 AE.
yeah, so it is delta Y is equal to delta L sine 60, which is PL by root 3 AE to root 3 by 2. So it is PL by 2 AE. So this is what we should get. So if we take P as 10, let's take P as 10. Okay, this is fine. So this is a test case we can compare with. There will also be a horizontal displacement that is difficult to get because you have to rotate it this way. You have to look at the other one, so it's fine. So this rod is moved to restrained. It will also rotate a little bit. So it will also rotate a little bit. So yeah, we have to solve it fully. There's no other way. Okay. So this, rather than doing this, I'll let me tell you something. We'll use the Castigliano's theorem. That's way easier. So get the strain energy. What it is? It is
Summation PKL by
yeah, summation over all elements.
PKL by AE.
PKL.
P
Okay,
square.
no, just as we did for the beam, what it is P
P
square
square.
by 2 AE dx. And all the elements are having the same length. So you can just write it as, so it is just P square L by 2 AE summed over all elements. So it is Pi Li square by 2 AIEI. And in the first, in two elements, we have P by root 3. So yeah, P is the force. Let me make it F square by 2 AE. So in two elements, we have P by root 3. So it is P by root 3 square L by 2 AE into 2. And the other element we have p by 2 root 3. P by 2 root 3 whole square L by 2AE. What it is? So take 1 by 2AE out and take P square out. L also you can take out. So it is 1 by 3 plus 1 by 4, 4 into 3 into 2. Yeah, 1 by 3 into 2 plus 4 into 3. So take 3 also out. So you get P square by 2EA. You get a 1 by 3 out. So you get 2 plus
1 by 4.
1 by 4. So it is 7 by 7 P square by 6EA. No,
9,
7 P square by 9.
9 P square.
Oh yeah, sorry, 9. Sorry. 9 P square by 2, 3, 4, which is 24. I can simplify this. This is 3P square by 8EA. Now, what is the load point displacement? It is rho P. So it is 2 times 3P by 8EA. So it is 3P by 4EA. Yeah, there's an L everywhere that you have to. Yeah, so it's 3PL by 4EA. So here we got something wrong. I guessed it because not only that the shortening is there, but it also rotates. It rotates without without causing any strain, and that rotation is given by the movement of the right side member. So it will be more than that. If you restrain this, if you allow this not to move horizontally, then it will be P by 2. It will be stiffer. Right? So we can check both the cases. So in this case, it is. So what happens if you don't allow this? This member will not have the contribution. This member will not contribute. Only the first one will contribute. There you will get P by 2. So yeah, so we'll see. We have to check. The answer at 3 should be 3PL by 4EA. Now let us code it. Let's code this. Okay, so I've also given um, a, a small thing to plot the truss. Okay, so this part I've already done, but in case, okay, let's not do it. Right, let's. Okay. Yeah. So this is basically that problem. Now I'll just, this will be A. This is the beams code. I'm just going to change it. So nodes and elements will start fresh. Bound nodes also will start fresh. Load is fine. Force is fine. Assemble, instead of I, you'll have A, E, F. You don't have plot beams, you'll have plot truss. That we can do later on. Okay, so let me share this on the. I should share it on the classroom. So let me do that first. Sorry, not assignment. Oh, what is this? Question. Material. Right. Truss problem. Vote for session 4. Yes, problems. I'll put this under quotes. Yeah, so you can, as usual, you can open it and then you can make a copy in your drive and then you can edit it. This which I just posted. So you can do that. In the meanwhile, I'll start editing this, right? So first step, so leave the plot truss function that I have made it and it will work. Okay, so this you can be sure this will work. Now let us go to the first part. Let's take this problem. Let's take this problem. Now, as usual, one of you can tell me the node. Oh yeah, nodes we didn't decide. What are the node locations? We can write here. Yeah. So what is the nodes matrix for this problem? Trusses like this. We say origin is here, 0, 0. What is this point?
L, 0.
Okay, this point.
L by 2,
Root 3 L by 2. Right?
yes, sir.
This is the height of the equilateral triangle, so it is root 3 L by 2. So the nodes matrix will be, which is this is first node, this is second node, this is third node. It will be 0, 0, L by 2, 0, L by sorry, L, 0, L, 0, and L by 2, square root of 3 by. Okay, what are the elements? In Python format?
0, 1,
Yes.
1, 2, 2, 3.
Do we have a 3? The highest number can be 2, right? Because it's 3. So we cannot have 2, 3.
Okay, so 2, 0.
2, 0. Yeah. This is the first element, second element, and third element. 0, 1, 1, 2, and 2, 0. Okay. We can fill that in. So nodes, as you said, it is 0, 0, L, 0, L by 2, NP. So whenever you have to take square root, use this NP dot sqrt 3 divided by 2. So for square root, you need to use the NumPy library. And elements, you can say it is first element connects 0 and 1. Second element connects 1 and 2. Third element connects 2 and 0. What are the boundary conditions for this problem? At 1, I'll also write it here. Boundary conditions are what? So here it is fixed and here you have
0, 2,
roll.
2,
0,
1, 2, 2, 1, false, 2.
Very good. So we'll do that. This is 0, true, 2, and 1, false, 2. Load is 10. Load will just take it as 10. Forces. So what will be the force matrix for this? So this has how many degrees of freedom totally?
6 degrees of freedom.
6 degrees of freedom. So force will be what? 0, 0. Here no forces are applied. Here no forces are applied. So 0, 0. Then
minus P, 0.
0. No, wrong. It's not minus
0
P0.
minus P.
Yeah,
0
0
minus.
Yeah. So it is size 6. So we'll fill everything with zeros. Then in the 6th location, we'll put minus P. So Python, it is 5th location. Next, we are going to assemble the global stiffness matrix. So you need A, E, nodes and elements. We'll go to that point. So we'll go to assemble. So so this is the so as I said, assembly is almost the same as beam, because this 2 degrees of freedom per two nodes per element and 2 degrees of freedom per node. So it is very similar. So first line will not change. It is just num nodes is equal to length of nodes. That's not going to change. The size of the stiffness matrix is 2 times the number of nodes. That's also not going to change. Then we are initializing. So the initialization part, there's no change. Initialization. Next, what we are doing, we are looping over all elements. Loop over elements. So what did we do last time? We said we called something as the current element. So deal with the current element. Deal with the current element. So we found node 1 and node 2 of the current element. Is that enough? No, no, we want, there's no nodes of node. How do you find the length? Yeah, you can tell me the code for find the properties of the element. What are the properties? Length and what are the two
Angle.
properties? Angle.
Length.
So how to find, yeah, how to find the length?
It is square root of x2
Yeah,
minus
so
x1.
yeah, so for that first we need x2 and x1. So let me say x2 is nodes of why x2? We can start with x1. So what is x1 and y1? We'll do one by one. X1 is what? How, where did we store x1? Yeah, in nodes matrix. In nodes matrix, corresponding to a node number, the first entry is x1. Second entry is y1. So it is in the nodes matrix.
Node 1.
Yes, node 1 and 0th entry.
Yes, sir.
So x2 is nodes of
Nodes of node 1, first entry.
node 2. No, node 2. So this is x comma y. So x2 is the second node x coordinate. So it is this one, right? Node 2.
Yes, sir. Node
0.
2, 0th entry.
Yeah. Y1 is nodes of
Node 1,
Node
first
1
entry.
first entry. And y2 is nodes of
nodes of node 2 first entry.
first entry. Yes. Very good. Now we can find the length. So as I said, for square root, use np.sqrt. I should zoom it so that you can see clearly. np.sqrt. Then what comes inside? x2
minus x1
the whole square
star
plus y2 minus y1 star 2. This will give the length. Then what should we do? We need alpha. So for finding alpha, let me write down a function. Let me check. I think there is a function np dot. I don't know if it will work. There is a straight. I said we need to check the this one, right? But I think there is a function arctan2. Yeah, I think this helps. Yeah, so this arctan2 gives the tan inverse, choosing the quadrant correctly. So if you just take tan inverse, which is arctan, you cannot differentiate between whether it is in first quadrant or the third quadrant. So so here our numerator is y2 minus y1, denominator is x2 minus x1. So other thing that we can do is we can write our own function to check whether if y2 minus y1 is greater than 0 and x2 minus x1 is greater than 0, then it is in first quadrant. If y2 minus y1 is greater than 0, x2 minus x1 is less than 0, it is in second quadrant. So we can do that. But when the function is directly available, let us just use it. Right? Let's use this function. Yeah, good that I remembered it. So use this function np dot arctan2, which takes two arguments. It says it will return the tan inverse of x2 minus x2 by x1. So numerator comes first and denominator comes second argument. Okay. So, and it returns in radians. So what should I put here?
y2 minus y1
y2
divided
minus
by
y1.
x.
No, there's no divided by.
X.
There's no divided by. That it will do. So it's saying if we give x1 comma x2, it will find the arctangent of x1 by x2 with the current quadrant. We don't need to do the division. So we have to give it the two arguments. Yeah, it will do the division. x2 minus x1.
X2.
But alpha, this is the previous code, delete it. So next, what do we do? Get the element stiffness matrix, right? So I'll call it a small k. Get, what did I call it? What did I call this function? Truss stiffness. And what are the, so just copy paste this. So it takes in area, Young's modulus, length, and alpha. Alpha we are computing, and it will return the stiffness matrix. What is the size of the stiffness matrix?
2 times length of.
No. This stiffness is local stiffness matrix, element stiffness matrix. For a truss element, what is the size of the stiffness matrix?
4 cross 4.
4 cross 4. Okay. So this is fine. Now let us go and edit the truss stiffness code. Okay. So if you remember, what did I have here? This is our truss stiffness matrix, right? It is a transformation Q transpose K dash Q. So first step is stiffness in axis aligned coordinates, which we call as K dash. So I'll write it as K dash is equal to what?
AE by LE.
You cannot A star
E divided by L.
Star. I'll make a matrix np dot array. Okay.
1
now,
minus 1.
No, it's not 1 minus 1. 1, 0, minus 1, 0, because you want 4 cross 4. If it is just 2 cross 2, you can just do 1 minus 1. So it is 1, 0, minus 1, 0. Then
0, 0, 0, 0. Minus 1, 0, 1, 0. Then 0, 0, 0, 0.
Then 0,
0,
0,
0,
0, 0. Okay. Next, we need to do the transformation matrix, which is Q. Okay. This is the transformation matrix. This transpose of the transformation matrix. This is the transformation matrix. So let's do Q. So what is? Let's call it. So just for simplicity, let me say again cos and sine functions. You have to use the NP library. So I'll say C is equal to NP dot cos of alpha, and S is equal to NP dot sine of alpha. Now what is Q?
C minus S 0, 0.
No, you should be careful. This is Q transpose. We are doing Q transpose K dash Q. So Q is this. So it is C.
CS S 0, 0. Minus S C 0, 0. 0, 0. CS.
Yes.
0, 0. Then
Minus S comma C.
Minus yes,
yes.
C.
Yes, correct. Yeah. I should have put it this way. So it's big. Okay, so this is fine, right? This. So you got the transformation matrix. What is the third step? You have to do the local to global transformation. So how do we do it? Q transpose K dash Q. So we'll do that here. So how do I do matrix multiplication? Now I'll call this K. So this is K dash. This is K dash. I have K dash and Q. Now I have to do this. So I'll say K is equal to, what should I do now? What should I write now?
NP dot
Transpose of Q. NP dot
transpose
of Q. Then
dot K dash
K dash. Then dot Q.
Q.
Yes. Right. So this is the you take Q transpose, dot it with a product of K dash. So this looks like three things multiplied. So it's like you multiply these two first. So you do K dash dot Q first. Then to that product you do you dot with Q on the left hand side. So this is what you're doing. So return K. Okay, very good. So now when we write big codes, it is always advisable to check it whenever we write a small piece. Okay, so I'll check this. So if our angle is 0 degrees, taking this time. Okay. So if our angle is 0 degrees, alpha is 0 degrees, length is 1, AE is 1, we have to get the K dash matrix. So we'll check that. Yeah, so I'll compile this function first. Okay, so this is our function to get this. I'll compile this function first. It is compiled. Now let us see what it is returning. So I'll go down and I'll type here truss stiffness of A is 1, E is 1, L is 1, and then let me take alpha 0. So it's a horizontal truss member. It has to return the bar element stiffness matrix or truss element in local quantity. Let's see what it returns. So it's giving 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0. Now suppose I make it 90 degrees. So it has to be in radians. So np dot pi by 2. Okay, this minus 33, minus 17, they are all basically zeros. So it's 0 0 0 0 0 1 0 minus 1 0 0 0 0 0 1 0 minus 1. So it's like rows 1 and 3 and columns 1 and 3 are swapped with rows 2 and 4 and columns 2 and 4. So that's also correct. So whatever was horizontal became vertical. So it's just a rearrangement of columns and rows. That's what should happen, and that has happened. That is what has happened. So the element stiffness matrix computation is working correctly, or at least there are no big mistakes there. Then what do we do? Come back to assembly. So we are telling this. Then I said we have to do some assembly operation, retain the old code. Okay, so as I said, use the same code because it will work. The logic is the same. So yeah, retain the same code. Then come to boundary conditions. For boundary conditions also retain the same code. So only thing is it was displacement and rotation degree of freedom. Now I'll rename it as U1 degree of freedom and U2 degree of freedom at every node. So here, if U1 degree of freedom is true, if I have to restrain this, then corresponding to U1, what is the row ID? It is 2 star the node number. then these operations are the same. So instead of rotation, you have u2 degree of freedom. That's all. Nothing else will change. Okay. Loop over all the boundary nodes and enforce the boundary conditions in this format. Then finally, we are putting it all together. We called the assembly, so it will return the assembled stiffness matrix. Then we are calling it to enforce boundary conditions. It will enforce the boundary conditions. And then we are solving it finally. So it is f of 5. So yeah, this is also fine. So the problem is put together very well. Let us hope there will be no mistakes. Let us see if it works all right. Now let me delete this and I'll do run all. Okay, so here there is some issue. Enforce boundary conditions. Okay. I node is where is it? For I node in bound nodes. List index out of range. Why is it out of range? I node of. Oh, there are two. Yeah. So there were two sets of brackets. That was the issue. Let's rerun it. Yeah. So it ran without any issues. Now let us see what U is. So it is 0, 0. This is the horizontal displacement of node 2. And this is the horizontal displacement of the topmost node. And this is the vertical displacement of node 3. So this is what we wanted, right? So I calculated it as 3 by 4. What was it? 3 by 4 PL by. Yeah. 3 PL by 4 EA. So P is 10, LEA is 1. So it is 3 by 4 of 10. So it is downwards. So we get a minus 7.5. So that's it. We have solved the problem. You can also test it against more complicated problems. So I have an example in the slides. You can see this, right? So maybe this you can take it as a homework. Can solve it manually. So yeah, it's from a textbook. So it's this. Okay, quickly, what is the static indeterminacy of this?
It's a truss, no, sir.
No, it's a truss. Right? It's not difficult, right? You have 1, 2, 3, 4 joints. So 4 joints means it will give you 8
One,
equations.
sir.
It is 1, yeah. So 4 joints will give you 8 equations. There are 4 members, and then how many reactions? 1, 2. Here 1 reaction. Here 2 reactions. Here 2 reactions. So 9 unknowns, 5 reactions, and 4 member forces, and you have 8 equations. So it is 1. So treat anything. Maybe this the horizontal force at B. You can treat it as you can treat that as an unknown. Then solve, get all the member forces in terms of the unknown, then use the Castigliano's theorem. So the differentiation of strain energy with respect to the unknown force should be equal to 0. Get the unknown force, and then you can solve for the unknown force. Once you get the unknown force, you can get all the displacements. So this is quite hard. It's quite hard to do it manually. So if you want, you can solve it manually, but since the areas are also varying, it's a little difficult. So you do one thing, just take all the areas to be 20. I'll post the homework on the thing. So make everything 20, and other dimensions are okay. 8 and 6 is fine. You can solve. So I'll post the corrected version. I'll say this. I'll make the areas equal. I'll make the Young's modulus equal, and then you can solve it. Okay. Now, so this is a statically determinate problem. Suppose I make it indeterminate. say I make it indeterminate. Maybe say benchmark 2. Let me make it indeterminate. Let's have it this way. Let us fix this side also. And then let me apply a vertical force. That I'm fixing this, It is not a roller, so it is indeterminate to 1 degree. So don't use any force method of solving it because it's going to, we won't get a solution. It's going to be very hard. Instead, just directly use the displacement methods. So we're applying a force P here, and this is structure is symmetric. So this node you can solve everything. So here the force will be same thing, P by root 3. This will be P by root 3. This will have some unknown force, forget about it. It has some force. We don't need to worry about it. But here you can use what I said. So here, because the structure is symmetric, this point cannot move to the right. So every displacement will be only by shortening of this member and some slight rotation. So if it moves down by a value delta, if that point moves down by some delta, it is because, so initially the member was like this, finally the member is like this. We can project this way. So how much is this? This is this is some delta theta. This is theta. It has rotated by theta and it has shortened by some amount. So this is delta L. And this angle is what? If this angle is theta, this will be 90 minus theta plus delta theta. This angle will be 90 minus theta. So what is delta L? Delta L is equal to, yes, delta L is equal to small delta times cos of 90 minus
Theta plus delta theta.
theta plus delta theta. So it is nothing but delta sine theta plus delta theta. So this sine theta plus delta theta will be approximately, when deformations are small, it is just delta sine theta. And theta, take it as pi by 3. So our delta L will be delta sine pi by 3 is root 3 by 2. Yeah. So delta, so the vertical deflection will be delta L 2 delta L by root 3. But what is delta L? It is 2 times PL by AE, right? PL by AE. No, FL by AE. F is the force in the member, in that member, but F is P by root 3. So it is 2PL by, that's a root 3, so it is 3 AE. No, so in the case where you are fixing the 2, you should get 2PL by 3 AE. Now let us check that also. That's a quick check. So this is statically indeterminate. Previous problem was statically determinate. So in this case, everything is the same. You see, only the boundary conditions will change. So what is the boundary condition in place of? Yeah, can you tell the change in the boundary condition?
In place of false, true will come. So
True will come. Yes. Okay. So now let us solve it. So you get it 6.6667, which is 2 by 3. Now, if you want to visualize the deformed truss, you say plot truss nodes LMs U. Oh, scale factor. Scale factor is, let me just take one. 6, right? No, I have to scale it down because it's very big. I'll make it 0.1. Right? So this is, the loads are unreasonably large. Let me make it 0.0 or 0.02. So this is the deformed shape. So you're applying a force there. At left and right bottoms of the triangle are fixed, they cannot move. So this point directly comes down. And for the previous problem, what do you expect? It has to move right side, right? So this will be false. Now I'll run everything. See, so that roller is moving towards the right and the top is coming down more than the previous case. Now we can take any complicated. So this is the power of this coding, right? You can take any complicated 10-member truss. Just 10 member is not really complicated. Say some very big physical truss. Say, for example, you can take the roof truss of a building in your industrial building in your college campus. Take any roof truss, right? You can take any roof truss. Apply point loads wherever. Say, suppose there's a roof truss that is supporting a sheet. Right? If you have some workshop building or some industrial building, you'll have a roof truss. That will be a Pratt truss. You'll have parallelograms with one diagonal specified, one diagonal member like this. And on top, you will usually have some kind of sheeting or something. So approximate the loads of the sheeting by some point forces onto the panel points. And maybe you can do this. Say if some of you wants to do a project or something by the end of the workshop, using all the concepts that we studied in this, trusses, frames, nonlinearity, you can do one such analysis. So use the codes that we developed, use these codes. We'll further develop when we do frames in the next session. It's late today, so I thought I can finish frames, but frames is very simple. In place of a 4x4 matrix, you have a 6x6 matrix, and everything is very simple. It takes hardly half an hour. You can do it. So you can try doing it. There can be mistakes, but I'll also do it. Then we are into nonlinear problems. So we are a little late. By 6 hours, I should have finished the linear part, but it has taken 8 hours and we are close to completion. So maybe it will take 9 hours. So I have to trim a little bit in the nonlinear part. I cannot do everything that we planned. Maybe we'll stop with buckling in nonlinear. So I think we have to compromise a little on the nonlinear part because I went into some details of the coding. So that's okay. I think we can stop here. So you just make use of.
Sir, no need to have a discussion, but that materials will you share that so that we can go through and we can contact you if we have the doubts in the part which were not discussed in this workshop.
Okay. So you're telling me that if I'm skipping something in the second nonlinear part, I can share the slides or something so that you can use it. Is it?
Yes, sir.
Okay. I'll do that. Yeah, no problem. Because even in this case, I may require maybe 2 hours extra that we can plan. Apart from that, even if we have the 2 hours extra, I think we won't be able to finish nonlinear fully. That's what I feel. So let's not extend beyond it. I'll share the notes, maybe even the codes, so you can work through it. And you can, yeah. By the time you get your certificate or something, maybe you can see if there's any issues, you can ask. And this code will be interesting. You can play with this truss problem code because you can just and use the plotting, right? Make use of the plotting, and you just play with it. Take any truss, take any physical truss that you see, apply loads, boundary conditions, and see how it deforms. You can also post process and get the member forces, right? Go to every element, get the nodal displacements. That you refer to the way how I computed the moments, bending moment diagram. Similarly, you can draw an axial force diagram for trusses. So that also you can do. So yeah, the code is already uploaded. You can make a copy and make your changes, and then you can. I'll give because it's difficult to learn it without doing by yourself. So I'll definitely give some homework with trusses and beams, or trusses and frames. So I'll upload some homework before next week, and you can solve. You can solve and submit. So yeah, I think this is the end of today's session. If you have any doubts, you can ask.
Thank you, sir.
Yeah. Thanks for attending.
Thank you, sir.
Yeah. Thanks for attending. I'll stop recording now.